Well, hello, good people. Today I have a little bit of a demo to show you. We'll see how this works. This is my classroom, by the way. Okay, here we go. Here I have a little bit of a setup where I have, oh, sorry to make this so whiplashy. I hope you don't get motion sickness. Okay, here I have a little setup where I have a battery right here. That battery is connected to a light bulb over here. That is a little bit hard to see. Okay, connected to a battery right there. Or connected to a light bulb right there. Then it's connected to a light bulb right here, then a light bulb right here, and finally it's connected back to a switch over here. Now I'm going to go ahead and flip the switch. And you'll see that all of the light bulbs glow. What is very hard to see is that all the light bulbs are glowing very dimly. There they are. And now over here, actually, wait, sorry, I want to stand back over here. Thank you for coming along with me on this journey. Okay, over here I have another setup. In this setup, I have a battery. This battery is connected to a switch over here, and then we have a light bulb here, a light bulb right here, and finally a light bulb back here. Now what I'm going to do is I'm going to flip the switch, and you're going to see all the light bulbs turn on. Here we go. And there you can notice, it's hard to see here because you're on a little computer screen, but they are all glowing much brighter than the other light bulbs before. Now here's what I'm going to do is I'm going to unscrew one of these light bulbs. I'm just going to unscrew this one, and I want you to notice what happens to the other two. What you should see is that you should see that they stay lit, but they actually glow a little bit brighter. Watch what happens as I unscrew this one back in. Did you see them get a little bit dimmer? Now, back over to my other circuit over here. If I look at this circuit, I'm going to go ahead and close it up. You can see the light bulbs glow much dimmer. I'm going to unscrew this light bulb right here, and I want you to see what happens. All the light bulbs go out. Here on this table, I have two types of circuits. This one, all of the light bulbs are on the same path together. And, wow, sorry, this one over here, you have little light bulbs connected by little loops that all kind of loop back to the battery there. These two types of circuits are called series circuits and parallel circuits, and that is our topic of the day. Today we're talking about series and parallel circuits. Now, I'm going to go turn on the lights, I'm going to pause the video, and I'll be right back with full brightness. One moment, please. Okay, we've got full brightness here. I have my pen and we are set and ready to learn. Let's talk about series and parallel circuits. Now, what you just saw were two examples, one of a series circuit and one of a parallel circuit. We will describe all the characteristics of each, but before we do, we got to talk about some symbols here. We're going to learn how to draw series circuits and parallel circuits, but there are a few characteristic, or I should say standard or conventional symbols that we use to draw circuits. These symbols will be used to draw what we call schematic circuit diagrams, and they'll help us analyze circuits, they'll help us understand how a circuit is set up, see how the current flows, and all those kinds of things. Here are the symbols that you need to know. First, you need to know that a straight line like this means a wire. Second, you need to know that if you want to draw a little switch, we can draw a little switch by drawing a little line, a little dot, bloop, just like this, and there, that's a little switch. This right now, this little diagram shows you an open switch. If you want to draw a closed switch, you would draw a little line like this, and you would draw that basically like this little lever gets flipped down. This is a closed switch. Then we've got some other symbols here that we can use. One symbol is a battery. A battery. Wait, let me write this a little bit lower. A battery looks something like this. You have a long line next to a little short line. The short line here represents the low potential terminal of the battery, or the negative terminal of the battery. And the long line represents the high potential terminal of the battery, or the positive terminal of the battery. The next thing that you need to know is you need to know a little bit about a resistor. We draw resistors, wait, let me try this again. We draw resistors like this, sort of. It's like a line with a little squiggle in it, sort of like that is how I normally draw it. And this is a little resistor here. Now, generally, when we analyze circuits, we are going to assume, generally speaking, that the wires have no total resistance in them. If we want resistance in our circuit, we add an element that we call a resistor. Let me go grab one really quick. Stay right where you are, don't move. Here's a resistor. I hope you're enjoying your time. Okay, coming back. Okay. Whoa. Okay, let me show you some resistors. Okay, oh gosh. This is a resistor. You say, that looks like just a blue cylinder. That's kind of what it is. This is also a resistor. This one, you can see actually really nicely has these numbers printed on it. And these numbers tell you certain things about this particular resistor. This one, it's hard to read from your perspective, but I can see that this says 36.5 ohms right there on the resistor, which tells me the resistance of the resistor. A resistor is a little device that's used to add resistance to a circuit. Basically, what a resistor looks like is if you were to look inside this little thing, you would see that it's either, it has a few different, it could have a few different properties. First, sometimes they'll just stick a little material in here that has a higher resistivity, it has a higher rho. Second, sometimes they'll just take a really long, thin wire to increase your L and to decrease your A. They'll kind of just wind it all up in here in a nice little tight compact space, and there you go. That gives you a little bit more resistance. So we know that resistance is dependent on rho, it's dependent, which is your resistivity, it's dependent on your length, and it's dependent on your area. So they just take a little piece of stuff that's a little bit higher resistance and they package it up in this little deal right here, and there you go. That's a little resistor. Resistors can come in a lot of different shapes and sizes, but generally we draw them all the same way. The way that we draw a resistor is we draw it as a little squiggle in the line there, kind of like if I had a little bit of wire and I just kind of squiggled it up inside of there. That's a resistor. The last symbol that you need to know is the symbol for, no, don't do that. Sorry, 1 second. I'm getting way better at this, I promise you. It seems like maybe there is more room for me to improve, which there is, but I am improving along the way. The last symbol that you need to know is the symbol for a light bulb. A light bulb is actually just a fancy resistor. And so a light bulb looks like the resistor symbol, but then with a little circle around it. A light bulb is a resistor that resists current. When it resists that current, those little electrons are pounding onto other little particles, gets them all going, and those little things start to move. Hey, when they start to move, we get a little bit of light and we get a little bit of heat. And so, yeah, that's pretty much the gist of a light bulb, and that's how it puts out all that light and heat, is because it's just resisting that current, and that current makes all the little electrons inside there move. And that's the idea. Those are your symbols. Now that we are equipped with your symbols, we are ready to draw a series circuit and a parallel circuit. I'm actually going to pull up a new window here, even though I have a ton of space, because I kind of want to do everything on the same page here now that we have our symbols established. So I'm going to pull up a new document. We are going to start by talking about a series circuit, and choosing colors is so hard. Yeah, we'll go with blue. That's fine. Okay. Let's start by talking about a series circuit. When you think about the difference between a series circuit and a parallel circuit, what you should be thinking about is paths back to the battery. How many possible paths are there to get from the high potential part of the battery to the low potential part of the battery? How many different ways are there to get there? In a series circuit, here's the key, do write this down. In a series circuit, all of the different elements of the circuit are along the same path back to the battery. In a series circuit, all the different elements of the circuit are along the same path back to the battery. Let's draw a picture of a series circuit similar to the one that I had on my table. Here's a series circuit. Let's start by drawing a little battery here. It is connected to, oh my, I want to fix that. Please fix. Please fix that. Oh my. Okay. Blah. Okay. Okay, so sorry. In a series circuit, here's what we have. We have a battery that is connected to a little resistor here. Then we got another resistor here. Then we got another, oh no. Oh, darn, I need to take more breaks. Okay, we got a little resistor here. Then we got another resistor here. Then we got another resistor here. And that all makes it back to the battery like this. There are always a few things that I like to label on my diagrams, and you should do the same. First, I always label, well, one thing that I like to label is I like to label the high potential end of the battery and the low potential end of the battery. You do not need to do that. That's something that I like to do. So I like to label the long dash of the battery will always be my positive end. The tiny dash will always be my negative end. Then we label which way the current is going. The current will always flow from high potential to low potential. So I'm going to label the current as going this way. The next thing that I label is I'm going to name all of my resistors. I'm going to call this one R1. I'm going to call this one R2. And I'm going to call this last one, wait, I don't like my 2, R2. I'm going to call this last one R3. So there are my 3 resistors. Then I label the potential difference of the battery. I'm going to call that delta V naught right here. I'll explain why. Here I put I naught and here I put delta V naught. Naught just means little 0 there. I'll explain why I used the naughts in a second here. And this is my schematic diagram for my series circuit. If I wanted to include a little switch here, then I could include a little switch. I didn't draw one on my diagram, but I do have one on my lab table. So it might be helpful to draw a little switch in here like this. If the switch is open, then you'll get no current that's flowing. So something like this would show no current that's flowing. But if my switch is closed, something like this, then current will be flowing in that circuit. So there you go. That's a little series circuit schematic diagram. Now what we're going to do is we are going to talk through all of the different attributes, all the different characteristics of a series circuit, and along with it, we're going to write down some equations. Please ignore the bells. Thank you very much. We are going to write down a bunch of equations. Now, what's really important here is that you actually understand the concepts behind each of the equations and not just that you memorize what the equations are, because things are going to get a little bit more complicated after today. And so you're really going to want to understand how exactly do these equations work and where exactly do they come from. So let's start by talking about current. Here's a common misconception. A common misconception is that in a circuit, the way that a circuit works is that little electrons run out of the battery and then they run through the little wire all the way back over to the positive side. That's kind of true, but also kind of not true. The truth is that it's not that little electrons run out of the battery and run all the way around. The truth is that there are already electrons in the wire that are ready to go. Those electrons are in the wire and they are standing at attention. The moment that you flip the switch, those little electrons will start to march and they'll all start to march together. Now, here's something that's true is that all these little electrons, they're all like stacked up next to each other, all together in a little row. If one starts marching, the rest are also going to start marching. You're not going to have like one electron that starts marching and then it just kind of like runs into another electron and it stops. That's not what's going to happen. Is all of them are going to march together like little soldiers. And so they're all going to, once that current starts, or once that potential difference is applied, once the switch is closed and there's a potential difference, they will all start marching in the direction of the positive plate. And they'll all march together. This means that the current at one place in the circuit has to equal the current at another place in the circuit. If I'm looking right, let me change my color out here. If I'm looking right, hang on one second team, we're almost there. If I'm looking right here and I see 5 little electrons passing by me in a second, that means that over here, there also have to be 5 little electrons passing by in a second. And over here, there also have to be 5 little electrons passing by in a second. And over here, there also have to be 5 little electrons passing by in a second because everybody's marching together. This gives us an equation for current in a series circuit. And the equation for current in a series circuit looks like this. We say that the total current will equal the current through the first resistor, which will equal the current through the second resistor, which will equal the current through the third resistor, and so on and so forth for as many resistors as you have. That's true for current. Let's talk a little bit about resistance. When it comes to resistance, resistance is about how much this wire or how much this circuit is resisting the march of the electrons. You can think about each little resistor acting kind of like a toll booth on the road. It's going to slow down the traffic and cause cars to take their time. It's going to make everybody slow down if there's some serious traffic lined up. So here's what's going to happen. Each little resistor acts like a little toll booth, slowing down the traffic a little bit. If you have one little toll booth, that's not that big of a deal. But if you have two toll booths along the same path, well, that's going to slow down everybody even more. And if you have 3 toll booths along the same path, that's going to slow down everybody even more. So the more little resistors that you have, the more everybody is slowed down. For this reason, we say that as you add more resistors in series with each other, you are increasing the total resistance of the circuit. So we say that the total resistance of a series circuit is equal to, and I'm going to leave some space here, is equal to R1 plus R2 plus R3 plus ... for as many resistors as you have. Now there are a few different ways that we like to write the total resistance. One way that we like to write the total resistance for a series circuit is we'll write it as RS, like this, where R stands for resistance and S stands for series. And another way that we'll write it is we'll write it as RE, where E stands for what we call the equivalent resistance. The equivalent resistance is another way of talking about the total resistance. Here's the general idea of equivalent resistance is if I could replace these 3 resistors with one resistor that was equivalent to the 3 resistors, what resistance would the one resistor have that's equivalent to the 3 resistors? It's really just another way of saying what's the total resistance of the circuit. So we can write this as R total, we can write it as RS, or we can write it as RE. All mean the same thing. It's the total resistance of that series circuit. Next, let's talk a little bit about electric potential difference. When we talk about electric potential difference, we know the battery has electric potential difference, but here's something else that's true, is that you actually have to have an electric potential difference wherever, oh my, okay, one second. You also have to have an electric potential difference, and here I am marking everywhere. You have to have, you have to have an electric potential difference across each resistor. Here's why that has to be true. The resistor is kind of hard for those electrons to sludge through. They don't really want to go through it. So you have to have a potential difference. You have to have something that is pushing them along through that resistor. If there is no potential difference, if there's no downhill for them to slide on, there's no way they're going through that resistor because they say, no, that thing is providing resistance. I'm not going over there, and they won't go. So you have to have something that is pushing them through the resistor. That means you have to have a potential difference across each resistor. That means the potential difference right here, or the potential right here is a little bit higher than the potential right here. And the potential right here is a little bit higher than the potential right here. And there's a potential difference here and here. This gives us 3 little potential differences. There's a delta V1, a potential difference across the first resistor. There's a delta V2, a potential difference across the second resistor, and a delta V3, a potential difference across the third resistor. Each one has a little potential drop across it. That potential drop allows the charge to flow, or it pushes the charge through that resistor. Now, let's talk a little bit about how that relates to our total potential difference here. You could imagine that our total potential difference is like, actually I'm going to keep up with my, oh no, don't do that, please. You guys are getting a lot of songs today. Okay, so we know that the total potential difference is like the difference between a high elevation point and a low elevation point. So the positive end of the battery is up here. This is like a high potential spot, and the negative end of the battery is down here. It's like a low potential spot. And then all along the way, you start up at the highest part right here, and then the potential drops just a little bit as it goes over R1, and then it drops just a little bit more as it goes over R2, and then it drops just a little bit more as those electrons charge through R3, and then it comes back over here. And here we have the lowest potential place. These little resistors will kind of act like stairs. The idea is you start at the highest potential, then you drop a little bit from the first resistor, you go on your merry way through the wire, then the potential drops a little bit for the second resistor, and it goes on its merry way for a while through the wire, then it drops for the third resistor. And so you get 3 potential drops here, delta V1, delta V2, and delta V3, and each of these little potential drops kind of act like stairs on the way down to the lowest potential spot, which is this end of the battery. That means that because each little one acts like a stair, you can see your total drop in potential is delta V naught. And this leads us to an equation that looks like this. We say that delta, I gotta make myself small here. Why am I taking up so much space all the time? Obnoxious, am I right? Delta V naught is equal to delta V1 plus delta V2 plus delta V3, and so on and so forth for as many little resistors as you have. Take a moment here and pause. Can you explain to yourself what is the current like in a series circuit? What is the resistance like in a series circuit? And what is the potential like in a series circuit? Take a second and answer that question. Make sure when you answer that question that you can also answer why behind each of those different elements. Do you know why the current is the same everywhere in a series circuit? Do you know why the resistance increases as you add more resistors in a series circuit? And do you know why the total potential drop for the battery is equal to the potential drop across each little resistor? Make sure that those kinds of things make sense to you. One last little equation here, then we'll talk parallel. The last equation is you know a little bit something about Ohm's law. I'm actually going to put Ohm's law in a different color because it's so special. Ohm's law says that I equals delta V over R. That is old news to you. You already learned about Ohm's law in days of old, and by days of old I do mean like something like yesterday. So there's Ohm's law. Now we can apply Ohm's law to this circuit, and here's what we would say. We would say something like, okay, well, that means that I naught, I'm going to put this up here actually. That means that I naught is going to equal delta V naught. Your total current is going to equal your total potential difference divided by your total resistance. Well, we could also say that I1 is going to equal the potential drop across the first resistor divided by the resistance of the first resistor. And we could also say that I2 is going to equal the potential drop across the second resistor divided by the second resistance. And we could say that I3 is going to equal the potential drop across the third resistor divided by the third resistance, and so on and so forth for as many resistors as you have. And couldn't you also say that each of these are equal to each other? That gives you a little bit of a strategy here for finding the total anything or finding anything in this circuit. You could find the current in one place or the current in another place if you knew the potential drop in one place and the resistance in one place. Or if you knew that the current is equal to I naught, then couldn't you also find the potential drop across one place if you knew the resistance of another place? So that's the general idea, is that these 1, 2, 3, 4 equations should equip you to be able to find the potential across any resistor, the resistance across any resistor, and the current at any part in the circuit. Okay, that's a little bit on series circuits. Hey, before we move on to parallel circuits, can you answer this question? If I were to add another resistor here, let's add another one like this. Burp, 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 burp. I add another resistor into the loop. When I add another resistor, what is going to happen to I naught, to my total current? What's going to happen to delta V naught, to my total potential difference? Think about it for a second. Okay, here's what I'm thinking. I know that I naught equals delta V naught over the total resistance. If I add another resistor, I'm definitely increasing my total resistance. Increasing my total resistance will make my current less. So I know my current is going to decrease. But my potential difference is going to stay the same. Check it out. Delta V naught is based on the battery. And adding another resistor here isn't going to do anything to my potential difference for the battery. The potential difference across the battery is going to stay the same. What's going to happen is that now I'm going to have a new little resistor in here to share that potential difference. It's like I added in here an extra little stair. That means that all the rest of the potential differences are going to decrease just slightly because now everybody is sharing the same potential difference of the battery. So add another resistor in here. When I add another resistor, my current decreases, my total delta V naught stays the same, and my resistance increases. That is a little bit on series circuits. Let's talk parallel. New drawing. For parallel, let's use the color. Wow, it's so hard to choose. Let's use cyan for parallel. In a parallel circuit, all of the elements of the circuit are on their own path back to the battery. In parallel, all the elements of the circuit have their own little path back to the battery. In parallel, all the little elements of the circuit have their own little path back to the battery. Allow me to draw you a sketch, and you draw this sketch too in your notes. Let's draw a parallel circuit. I'm going to change up where the battery is because I can, because it doesn't really matter where you draw your battery. Then I'm going to draw here is a little resistor. Here is another little resistor. Here is another little resistor. Oh, I don't like that line as much. Okay, there we go. Now I always label my circuit. I'm going to label this R1. I'll label this R2. I'll label this one R3. This is my positive, my high potential end. This is my negative, my low potential end. So my current I naught is going to go this way. This is going to be delta V naught will be the potential difference across my battery here. And now everything is all labeled up and we are good to go. Let's talk about parallel circuits. We're going to break them down into each of its little characteristics. We're going to start by talking about current, same as we did last time. Let's talk about the current here. Current always goes from high potential place to low potential place. Now here's what's going to happen to the current. All the current will be marching this way, and then when it gets here to this point right here, the current will have to make a choice. Either it will have to choose to continue on this way right here, or actually I'm going to do this with a lighter color because that just sounds so fun. Okay, let's try this. Okay, either it will continue on this way like this, or it will split and go down through R1. The current that splits and goes down through R1, we shall call I1. It's the current that goes through R1. Then this current will continue on its merry way, but then it will split, and part of it will go down into I2, and part of the current will keep on going on its merry way. This current will then go through R3, and we'll call it I3, and then it'll make its way back to the battery. Here's what we say, is we say that because the current is going to split each time it gets to a branch, the total current unsplit is equal to each of the currents added together. This gives us our first equation for a parallel circuit. We say that I naught is equal to I1 plus I2 plus I3, and so on and so forth for as many resistors as you have in the circuit, since the current keeps splitting and going on its own individual little branch. That's the first idea. Now let's talk about resistance. Once again, you can think about resistors acting like little toll booths. But this time, the toll booths are on all different rows. Check it out. Count how many paths you have to get back to the battery. A little negative charge could go this way back to the battery. That's option 1. It could go this way back to the battery, that's option 2, through the second resistor, or it could go this way back to the battery, that's option 3, through the third resistor. It has 3 paths to get back. And if you added another resistor, you would be adding another path. Each little resistor acts like a little toll booth, but every time you add a little toll booth, you're also adding another way back home. And so the total resistance in parallel decreases as you add more resistors, because traffic will be able to make it back home even easier with more resistors because there are more paths. This leads me to an equation that looks like this. I say that 1 over my resistance in parallel, which, by the way, is 1 over saying, you could say this as RP for parallel, you could say it as RE for the equivalent resistance. Either one is totally great. 1 over the resistance in parallel is equal to 1 over the resistance of the first resistor plus 1 over the resistance of the second resistor plus 1 over the resistance of the third resistor, and so on and so forth. Now, this equation here shows that as you add more resistors here, RP is actually going to drop. We like that the total resistance is in the denominator here, unless we're trying to find the total resistance, and then that poses a little bit of a problem. If I asked you to calculate the total resistance, well, you would have to get this out of the denominator and back up into the numerator. Well, there's a sneaky little algebraic trick that allows you to do that. Here's what I'm going to do is I'm going to take both sides to the -1. And so I'm going to say, here's my little algebraic rearranging. You would not show this on your original equation, but I'll show it here. I'm going to say that my total resistance in parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus so on and so forth, all of this to the -1. Another way to write this is you could write this also as R1 to the -1 plus R2 to the -1 plus R3 to the -1, all of that to the -1. So that gives you a few different options on how to write that equation. All of these ways are totally fair and totally good ways to write it. That's a little bit on resistance. Now let's talk a little bit about potential difference. And I'm going to need some colors here. Let's go with a light green. Do you see how this spot right here is connected, this is my low potential end of the battery. Do you see how it's connected to this side of this resistor? It's also connected just by wire to this side of this resistor, and it's also connected just by wire to this side of this resistor. Likewise, on my high potential end over here, oh no, not that, please, don't do that. That's annoying. Do this. Yay. Okay, do you see on this other side here, here's my high potential end. Do you see that the high potential end of my battery is connected to this side of this resistor, this side of this resistor, and this side of this resistor? Here's what that means. One side of each resistor is connected to the high potential place, and one side of each resistor is connected to the low potential place. If I set up a little diagram here, if I have a high potential place, high potential, and I also have a low potential place, we'll trade it out for green. I also have a low potential place, like this. Then each little resistor drops from high potential to low potential. And so one resistor, oh no, don't do that. Please come back. No, don't do that either. Please stop doing that. That is no fun when you do that. No one enjoys you when you do that. Okay. Let's try. That was really cruel. I'm sorry. I shouldn't have spoken like that. Okay. So let's go here to here. So my first resistor, R1, goes from high potential to low potential, like this. My second resistor, R2, is connected to the high potential place and the low potential place. And my third resistor, R3, is connected to the high potential place and the low potential place. So I get 3 voltage drops, delta V3 here, delta V2 here, and delta V1 here. And if I were to talk about delta V naught, well, delta V naught would be the total difference between the high potential place and the low potential place. And that would be my, oh, no, I don't want that. That would be my delta V naught, is from high potential to low potential. What you'll see here is instead of having a mountain and having like stairs where each little resistor acts like a little stair on the way down to the low elevation point, instead, each little resistor acts like a total drop. So there are 3 paths down the mountain. One that's a steep drop, another that's a steep drop, and a third that's a steep drop. This leads us to our final equation for parallel circuits, which is, I don't know why I was trying to do that, which is the delta V naught is equal to the potential drop across the first resistor, is equal to the potential drop across the third resistor, is equal to the potential drop. Why did I skip to third? My brain just might like the number 3 today, I suppose. And then that's equal to the potential drop across the third resistor, and so on and so forth for as many resistors as you have. And those are our 1, 2, 3 expressions for the 3 different attributes of the circuit for the current, for the resistance, and for the potential difference. Can you please explain to yourself in your brain right now what is the current like in a parallel circuit, what is the resistance like in a parallel circuit, and what is the potential drop like in a parallel circuit? And then can you explain for each of those things why that's true? I'll give you a second, pause the video, explain it to yourself, make sure that you know this for sure. Okay. Now, once again, like last time, we can use Ohm's law to kind of parse this out a little bit. If you wanted to talk about I naught here, well, once again, you could say that I naught is equal to delta V naught divided by your equivalent resistance here. You could also say that I1 is equal to delta V1 over R1. Likewise, you could say I2 is equal to delta V2 over R2. And lastly, you could say that I3 is equal to delta V3 over R3. If you wanted to talk about I naught, you would have to add together each of these 3. And so you could totally do that if you wanted to. Now, that gives you a lot of different formulas for talking about a parallel circuit. A few things that I want to talk to you about. First, do you understand why, if I were to take this little light bulb out, if I were to unscrew it, can you explain why the other ones would still stay lit? You should say, well, yeah, sure, Miss Wilson, because if you unscrew this little light bulb here, there's still a path that the electrons can take to get back to the other side of the battery, so charge will still flow. That is not true in a series circuit. In a series circuit, everybody is along the same path. Oh, wait. Wait. Okay, sorry. In a series circuit, everybody is along the same path. So in a series circuit, if you take out one of the little light bulbs here, well, you just wrecked the path back to the battery. There is no longer a path back to the battery if you take out one of these circuits, or if you take out one of these resistors. So then everybody shuts down and there's no more current flow. You gotta have a complete path in order for current to be able to make it back to the battery. I take out one of these resistors, I still got 2 complete paths back to the battery. Back in the day, they used to make strands of Christmas lights. They used to wire them up in series. This was very problematic because if one of the hundreds of light bulbs that are on your Christmas tree burnt out, then they would have no idea which one it was because all of them would burn out. And so you'd have to go through and individually test each little light bulb to see which one was the one that was no good. But now they don't do that anymore. Now they wire up your Christmas lights in parallel so that if one of them goes out, well, that one goes out, but the rest of your 100 light bulbs still stay lit. And so then you can still see your Christmas tree sparkling in the window at Christmas time. That is a little bit on series and parallel circuits. I do really feel like I had one more thing to tell you, but I just can't really oh, yes, okay, good, wow, whew. Oh gosh, I'm so happy I remembered. One last little thing to tell you about parallel circuits. Do you notice here how since delta V1 and delta V2 and delta V3 are all going to be the same? Let's say that for R3, I just had a very, very serious resistor here, like something that has way more resistance than the other ones. I'll draw it all thick so that you can see it's so serious. Look how serious that resistor is. It's like crazy resistive. I have a super resistive resistor here. What'll happen is because this one is so resistive, but the potential difference is the same for all three. Delta V will stay the same. This increases, and so my current decreases. And less of the electrons will take this path. Or another way to think about it is that the traffic will be much slower along this path, and so the current will be much less in that path. So you can see that the individual resistance of each resistor determines how much charge will flow along that path. That was my last thing for you. So we've talked a lot about parallel circuits. You've learned the three different attributes of parallel circuits, how current works, how resistance works, and how the potential works in a parallel circuit. We also talked about series circuits. In series circuits, we talked about their three attributes, the current in a series circuit, the total resistance in a series circuit, and then also the potential difference around a whole series circuit. And we also learned about how to draw schematic diagrams. How do you actually draw a circuit? Well, these are the symbols that we're going to use in this class. And those are also standard symbols, by the way. So you learned all of those symbols for your schematic diagrams. And that is really all for today. Tomorrow, when you come back, we'll be talking about what happens when you combine a series circuit and a parallel circuit together. I hope you have a wonderful, wonderful rest of your day. Bye, good people.